this is how the JK flip flop, which is the this is a JK flip flop, okay, which is the card above the SR flip flop, or the modification of the SR flip flop. How it works, as you've just seen, that is the R is the input in J and the QT dash, and the S is K and the QT, and the third input is the clock. This is the clock edge. So this will be connected to the positive edge. When it is negative, it is disabled. At the levels, it is disabled, but the edge, positive edge, will enable it. And when the positive edge is enabled, the JK flip flop will behave like this. These are the states. Except that there's a why we needed to modify it. It was happening like this, that for 1 and 1 in both set and reset, we were receiving an undefined signal. In this case, we see the complement of the previous output. This is happening because of the ANDing with the outputs of the two. You can see that up to here, if you just ignore the 3 input AND gates, this looks exactly like the SR. So now when we are receiving this, input fed into this back, QT fed into this gate, and QT dash fed into this gate. Same thing, except that this also is going into the first one. It's a 3 input AND gate, and this also is coming and going into the next one. And so in this case, we have got the option of receiving a table like this. Okay, so the same thing, 0 0, and it is a hold position, it's maintained. Then if the set is on, if the reset is on, okay, then reset signal. If the set is on, then set signal. On the other hand, if both the signals are on, then it toggles. How does it toggle? If QT, that is the previous one, is 0, it becomes 1. If it's 1, it becomes 0. So you have the option of having, this is not undefined anymore, you have the option of having a complement of the previous input. So you may ask, what is the, how do we, what is the point of this? Well, see, I'll show you the point. Let us say the output signal is a reset signal, and you want to change it. How would you want to change it? So reset signal is this, and you are at a position this. So you have to make this 0 and make this 1, like this. On the other hand, with the JK flip flop, all you have got to do is make them both 1. So whichever one was a 0, make it 1. Then whatever you had before would change. Okay. So it's a small operation. Make it so if it was reset or set, whichever is the case, correspondingly either it would have been 0 or 1 or a 1 and a 0. All you've got to do is make the 0 signal to 1. So you don't have to change the two signals. You do not have to change the two signals. You just make short work of it by changing the 0 signal into a 1. Immediately, whatever you were having before would change. So if you are having an off signal, it will be turned on. Having an on signal, it will be turned off. Okay. Somnath, is the video visible now? Okay. So where from did you not see? Did you understand this table? Did you understand why the JK flip flop is a cut above the SR flip flop? How we are toggling? Did you understand that part? Somnath, did you understand? Okay. So you see, in an SR flip flop, what would happen is that this would be undefined. But because of the input fit from the output of the two gates, we have an option of getting the complement of the previous input. What would that be? If it's a set, then it would be, if it's a set, it would be a reset. If it's a reset, it would be a set. What good is that? Let us say if you are having 0 and 1, and if you are having a reset, you want to set it to set, you have to come down to this position, say 1 0. And a 1 0 position, that means this has to be turned to 1, this has to be turned to 0. So obviously the signals will have to be changed in both the inputs J and K. In other words, S and R. So then only you have a set signal. But in this case, what is happening? What is happening? If you have a reset signal, you have a 0 and a 1, just change just 0 to a 1 and the signal will toggle. So by changing just one signal, whichever the case is, either the set or reset, whichever is 0, if you can change that one, the output will change. Output will change how? If it is a set signal, toggle to reset. The reset signal set, just reset signal, it will toggle to set. Just by changing one signal, you can switch between set, set, reset, reset, set, reset. That's a easy. Flip flop obviously is a bit more complicated. Definitely, you can expect that. But operation is so much easy. The toggling between the different states is so much more easy. So if you have a circuit where you have to provide set and reset signals one after the other, you can use the JK flip flop and toggle it easily. This is the glory of the JK flip flop. Now we'll look at another flip flop, the D flip flop. We have the D latch, the data latch, and you've seen the data latch. Now this is the flip flop. Data flip. Let's just have a look at the D latch. The it was here, and in this case, we're providing it with the sorry, not the edge. I beg your pardon. This was not the edge. This was the level. The level was here. That is the enable signal. The level was here, but we are not using enable here. These NAND gates, and the OR gates. We're not using enables here. What we're using? We're using enable signal in the form of a clock edge. Rest is exactly like a D flip-flop. D latch, beg your pardon. Okay, look at this. Just a modified SR flip-flop in the sense that the D is inverted and fed in the second one. All two input gates. Output of the first one going into output of the first one coming into the input of the second one, and the second input output gate, and the output of the second output gate fitting into the input of the, you can take it as the first input of the second input of the first output gate. So as an effect, as you can imagine, that whatever is D, a 0 or a 1, this will be kept intact. And this edge here, rather than the level, will keep the data flip-flop enabled for a small amount of time. So that you can get the data, then you can shut down the flip-flop, and when you want it, you can get the data, providing it to the edge, the positive edge of the clock. So for the little amount of time, the data will be enabled. So it won't stay transparent for a long time. Now you see the little bit thing here, that because of the, so these are all electric lines. They're coming into a transistor. They're nothing but electric signals. There will be some resistance here. So there is a propagation delay. When the signal comes in, it's not instantaneous. Neither is the clock edge instantaneous. Exactly instantaneous it is not. It may be a very small instant of time, but still instantaneous means then and there itself. That cannot happen. That is not logically, or rather physically, it's not possible. So whatever little amount of time it takes, it takes. So when the signal is coming in, see, and this edge is coming out, you have to calculate how long it is taking to come in. As we arrive at both ends here and here, and you have to calculate for how long the clock must stay on or will stay on, and then you have to calculate when you are going to have to put in the input, when you are going to have to activate the edge. This is calculated by way of how the propagation time is, or what the propagation time is through these channels of the data. By that you determine when you put a signal in D and when you put a signal in the form of clock edge, when you put a signal in through this channel. That you have to account for the propagation delay and the clock edge time, and so on and so forth. So you can imagine, look at the table here. So with the rising edge only, D is 0, output is also 0. With the rising edge only, if D is 1, it's 1. When the clock is at level or the clock is at negative edge, what data is there does not matter. There will be no output at the output side. There will be no output or garbage output, whatever.